Everyone want to get started?
Yeah. Yes, sir.
So we can move on, get this over with, get on to the next thing, whatever that happens to be. No, that's good. All right, I'm sure we're going to have some stragglers coming in, so as long as you don't mind, every time somebody new comes in, I'll start over. Is that okay?
Yes.
I don't want them to miss anything. Or should we tell them that their pink slip is in the back of the room? Something like that? That won't worry them? Okay.
I wonder if they work by like that.
No, we need those people. My name's Ken Smith, and I'm going to cover extending the capacity of MLC flash to increase total cost of ownership. The other name for that, of course, is ROI. Now, this is this is a product that we actually announced at Flash Memory Summit, but I didn't get a chance to talk about it, so I thought we could probably spend some time here, and so hopefully you'll find it interesting. So let's talk about, really briefly, flash in the data centers. So as a reminder, typical IOPS per drive for hard disk drives versus SSDs, I think everyone's pretty clear on this. There's certainly an advantage to having flash in the data center. Now, we also know that the price per gigabyte of flash is significantly higher than hard disk drives, so that's a hard thing to swallow. But of course, your typical IOPS per dollar justifies it for the segment that's looking for that higher performance. So you get about 5x better performance. Okay, so that's good. So some segment of the storage industry can take advantage of that. But what if you could triple the capacity of the same flash? Is that weird? It's like, what the heck are you talking about, Ken? You can't triple the capacity of something that's the same. How can you take a car with 5 seats and put 15 people in it? No, it's not a clown car. It's a real car. And we can put 15 people in that 5-seat car. Does that sound cool?
No.
No? You, pink slip, out. You're fired. Okay, so let's look at it again. Same equation. My typical IOPS per drive is the same, but my dollars per gigabyte drops by 3. So that's a pretty significant advantage, which means then my typical IOPS per dollar increases by 3, so now I'm more like 16 times higher performance per dollar. Okay, so this is interesting. All right. So, Kent, you're just making up some stories. You could have an hour's time in front of some nice people at this show. You're making it up. No? So a data reduction technology can help this situation. It can be used. So let's look. I hear from people all the time, all data is compressed today. You can't get anything out of it. Everything's at 100% entropy. Guess what? No, that's not true. We've done a lot of study on this. For example, this is an Oracle database. If you look at the Oracle database itself, actually look at the characters in the database, what is Oracle trying to do? They're trying to get you data quickly as possible. How do you do that? You don't do anything to it. You make it the raw data that you can feed right back up the pipe. So they don't do anything to make it smaller, to compress it, because that takes time. It slows the whole process down. So Oracle has only about 30% entropy. It's compressible 3 to 1. That's huge. Anybody know how many Oracle databases are out there? Okay, there's a lot. Okay, there's a lot of databases, which means there's a lot of data that can be taken to this 30% entropy. Now, just to kind of see where it fits within the scale of all the other file types, interesting that HTML has about a 3% entropy. What does that mean? I can only get 3% out of it? No, it means there's only 3% left. 97% of it could be thrown away, and you can still recreate exactly the same content. Okay, well, I think there's quite a bit of HTML in the world these days. Seems to be a popular thing, and similar forms to that. Looking, here's the Oracle at the 30%, but you can see other file types, executables, DLLs, 57%, 32%. That's all that's left. Well, where are executables and DLLs used? The operating system. So you put the operating system on, and a huge part of the operating system can be condensed down. Okay, this is great. So if I have any of these files in here, I have a huge advantage. Now, PowerPoint, XLS, DocX, and you can see down JPEG and MP3, they're getting pretty close to you've got all the entropy out of them. Okay, absolutely. I'm not saying 100% of all data can be reduced, but by the way, even 2% can have a huge difference if you're dealing with only 7% OP. Over-provisioning has a huge advantage, and it's not linear, for helping the life of the drive. Okay, so we've been using that in that direction, but maybe there's a way to use it in another direction. So what if we could compress all data on the fly? How would this be done? Well, there's going to be some issues, and then there are some solutions to each one of these. So let's we'll break it down. So no matter where you're putting your on-the-fly compression, right, or whatever you want to call it, all of them need some level of predictable entropy to some degree. Now, you don't have to have that, but it certainly helps. And the biggest problem is operating systems today don't understand the capacity can change. Primary storage capacity is always the same, no matter what. It's not like it's a tape drive where it's constantly changing. It's not an exchangeable device like a CD-ROM, DVD, that kind of thing, where it can have a different capacity. In this case, it's a primary storage device, so the operating system itself doesn't know. So if we look at how would we solve that, well, data centers do understand a lot more about their data, and they partition their data. They manage their data differently, so they could take advantage. And actually, we can customize the drivers inside the OS to take advantage. And there are already custom OSs that wouldn't be as difficult to change. You know, Linux is changeable, and certainly a lot of the mega data centers wrote their own OS. So they have total control over that. Okay, so now let's look at the CPU. I can have the CPU do all the work, but that's a pretty expensive chip to allocate to just taking care of that particular issue. And there is some limited max throughput that you're going to get, especially when you have multiple drives attached. So that's probably not the best solution. So instead, you'd probably want to make it a device-based solution. So it's all up to the device to do that work. So let's say, why don't we have the HDD do it? There's a lot of HDDs out there. The problem with the HDD is there's no variable mapping table. And what I mean is the HDD is storing data directly, one for one. The operating system and the HDD have a direct relationship where the OS believes it's stored. Effectively, the HDD is putting it there, and it can overwrite data directly, no big deal. The problem with something where you have a compressible system, now suddenly you could put more data. You don't have a one-to-one relationship. And so the hard disk drive would require a major re-architecture. Okay, so that's not going to happen anytime soon. So what about SSDs? So they already have a flash translation layer. Okay, that's cool. But they don't understand, they don't support a non-constant data size. So that's kind of a problem. You know, they have the non-one-to-one relationship, meaning where the OS thinks it's stored is not where the flash put it, because it had to store it somewhere else because it had to wait till the block was erased, et cetera, et cetera. But you would need some kind of complex flash translation layer that could account for the different data sizes. Okay, all right. And by the way, it gets more complex now when you garbage collect, when you have data placement questions, when you're block picking, the problem gets really complex. Okay, so it's not a simple problem to solve, but a 3-to-1 advantage would be huge. If I could get the cost down by 3 times, I could probably make some money off that. Idea. Okay, so if I have to have an SSD that supports a variable map size, what are the potential candidates? Anybody have any ideas? Now that I have the slide up, boy, it's a simple one. Anybody? No? SandForce controllers? They might have this ability. Huh? Yeah?
There is a formula?
Yeah. Well, in fact, how about the 1000 could do this technically? But by the way, we aren't advancing that technology. The SF2000 family can have this same capability. Certainly the 3700 has the same capability. So let's first talk more about what's happening here. So you have to have some kind of data reduction technology that also understands variable data sizes. Okay, so that's already built in because Durawrite already figured out how to do that. You know, that's the tough part. You know, people always ask, oh, Durawrite is just a compression engine, right? And for those of you who were, like I think half of you were here with me with Earl, no. To be honest, that's the simple part. The complex part is everything else behind it. So there's a whole lot more than I think a lot of people realize. So Durawrite already has that flash translation layer that accounts for that variable size data for both reading, writing, and the garbage collection. And it also manages spanning the flash page boundaries. Because when data comes in, you know, typical controllers, let's say they're based on a 4K transfer, and the flash is set up in 4K pages, wow, that's really simple. It maps directly. It's really easy. So you have to be able to account for, you know, the data coming in is not going to match the flash. And then you've got to figure out, well, when do I write to the page? Well, when do I store the next? And oh, should I you know, get this data with that data? It gets real tough. So it already takes care of all that. It supports that variable data length. And as well, each LBA can be a completely unique size. Okay, it needs to have that, yes. So the other thing is it needs to provide for multiple flash page sizes, right? As the code rates become more and more important, as the flash itself becomes more error prone, you have to be able to account for different error rates. And so that's also what Durawrite is helping take care of. And as well, Shield technology that we were talking about earlier with Earl. We also announced that at the Flash Memory Summit. So both of those work together to help take care of that issue. So LSI introduced Durawrite Virtual Capacity, or DVC. I may call it either one, depending on what I'm thinking of at the time. So DVC, for those of you local, it's not Diablo Valley College. That's what I always think of when I hear DVC. No, Durawrite Virtual Capacity. And so it leverages what Durawrite is already providing, but it does it in a different way. It does it, I like to say it does it backwards of what it's been doing for the last 3-4 years. And I'll show you that example. But in this case, if we, for example, had that Oracle database here, let's say that was a 512 gig drive with Oracle data on any other controller. It'd be 512 gig, right? You paid for 512 gig, you got 512 gig worth of Oracle data. But if you ran it through Durawrite Virtual Capacity, the same exact amount of flash would give you over 3 times that, over 1.5 terabytes of that Oracle data would sit on that same physical flash. 3x improvement. Wow, this is cool, Kent. Wow. Yeah, I know it's getting late in the afternoon. I forgot the sugar, I'm sorry. I'll try next time. So the lower the entropy, the more you get out of it, obviously. So this obviously creates that complexity I was talking about. You know, the OS has to be able to adjust to a constantly changing max capacity. Yeah, by the way, it can be done. It's already being done. So let's kind of look at the details of how this works. So I was talking about the core of Durawrite makes this happen. So let's look at a 128 gig drive, just to kind of simplify it. In this 128 gig drive, there's that much physical flash. And I'll show you 120 gigabytes is user data, and there's 8 gigabytes of over-provisioning. Typical 7% OP. Now, by the way, this is not your typical enterprise config. Those are generally in the 28%, but I'm just trying to simplify it. It's the same exact situation here. So normally, Durawrite takes that 120 gigabyte of, let's say it's the Oracle database. It makes it fit in only 40 gigabytes of space. Right? Makes it that much smaller. What does it do with the rest of the space? It gives it back in over-provisioning. Because the operating system doesn't have any idea how to deal with varying capacities, so it can't give it back to the user today. Again, this is just what Durawrite does today. This is the stuff we've had for the last 3-4 years. But that 88 gigabytes of extra OP, I go from 8 gigabytes to 88 gigabytes. That's a huge advantage. Performance goes way up. Endurance, way up. There's significant advantages from that. Okay, that's great. The drive will last a lot longer. But by the way, you still only get to put 120 gigabytes of user data. Okay, most people didn't complain. That's what they bought and paid for. But this drive lasts a whole lot longer. So that's good. That's what Durawrite does. So now let's look at Durawrite Virtual Capacity. I said it was kind of backwards. It does it the other way around. So we have our same 128 gigabyte SSD. 120 gigabyte of user space is where it starts. And it's got, let's say here, 8 gigabytes of over-provisioning. Right? Same exact two configs. Now in this case, with Durawrite Virtual Capacity, the 120 gigabytes is still down to the 40 gigabytes of space, just like in the Durawrite only configuration. But now you can put 80 gigabytes more. It gives it back as user space. So in the end, you can actually have 360 gigabytes of user data on a 128 gigabyte SSD using the Oracle database example. Is that cool? Yeah, wow, there we go. Wow, you get your 20 bucks later, finally. Okay. So the use cases, so how can we use this? So the technology can really be applied in two different ways. We've got both as native user data storage, as well as dynamic caching. And what I mean by that, I'll actually talk about each of these. So let's start with the native user data storage. This is where the user is putting their data. All right? This is what you're expecting as the flash space, as you get additional flash space, it goes directly to the user so they can put more data in. So the pros of this is the user capacity increases for that same flash cost. So that's a huge advantage. The con is it does require that OS change. Remember, Durrite on its own works independent of the OS. It gets that advantage for faster performance and longer endurance without having any operating system intervention. But in this case, if you need the user capacity increased from Durawrite Virtual Capacity, there has to be knowledge at the OS level to deal with that. So it's easier, as I mentioned, with Linux and custom OSs. There's a number of big mega data centers that build their own OSs that I kind of alluded to the fact that there are customers today even evaluating and using this now. And unfortunately, if I told you, I'd have to kill you, because they don't want anybody to know what they're doing. So suffice it to say, I can't say that I have deployments and evaluations if I don't actually have them. So I do have them, I just can't tell you about them. But the advantage seems pretty clear. A 3x cost advantage using the same flash. I mean, that's sort of the thing they're constantly looking for. Here, we just handed it to them on a platter. Okay, they're ready to go. Now, today you can see this in the LSI Nitro product line. They do support this as user data storage. And then some select SandForce-driven SSDs are also doing this right now. Those are the guys that are talking to the deployments that I can't tell you about unless I kill you. Okay. Now, dynamic caching. That's the other use case. This one's kind of cool, because in this case, there's no operating system change. Okay, well, let's talk about that. So in this case, dynamic caching, the additional flash space you get from Durawrite Virtual Capacity is given back to the application or hardware that's managing the flash as a cache. So for example, if you think of the LSI Nitro line has within the product set, all the controllers managing flash are managing just caching for hard drives that you hook up directly to the Nitro interface, right? So it's a combination of flash and hard drive controller. So in that case, it's caching all the rotating hard drives, and when they enable Durawrite Virtual Capacity, Nitro already knows how to deal with that variable flash size. Problem solved. Operating system doesn't care. So in that case, if they had 512 gigabyte of cache, now when that Oracle database comes through, they're caching 1.5 terabytes of data. So operating system doesn't know, the hard drives don't care, but suddenly you have 3 times the amount of data that's being cached off the hard drives. Huge advantage. The same system would cost 3 times more for that flash. And that's the majority of the cost there. Okay, so obviously the con is you have to have that integrated caching system. Okay, well if you have it, then it's not a big deal. Again, that's part of the Nitro product line, and there are some select SandForce-driven SSDs that are also working this, but in that case, that caching application is more of a host level, right? So that's another option, of course. And the host level is the application that deals with the capacity change. Operating system, again, doesn't know, doesn't care. So in the 2 markets, really the dynamic caching is really more of that enterprise focus. And then the native user data storage. Today, more enterprise focus, especially with custom OSs and Linux, or client environments with Linux. Now you won't really see this hit big in the client space. I mean, there's a huge advantage. Suddenly you could have 3 times the capacity for the same cost, but you're not going to see it until the Microsoft drivers go through that change, right? So already today there's a number of customers that are thinking this through, saying, okay, if I buy enough Microsoft product, I can probably influence them. And if enough get together, oh yeah, that can happen too. So lots of conversations going on in this area. I'm not about to predict when Microsoft's going to flip and they say, you know what, we need a standard around varying size capacity. It's happened before. Microsoft does make changes to the OS, believe it or not. So we'll have to stay tuned on that one. Okay, so clearly flash in the data centers is definitely expanding. You've got, we know that compression can greatly reduce the cost concerns of flash versus hard drives. I showed you that. There are certainly some major complexities around that, but that's where Durawrite Virtual Capacity addresses those issues. So as I mentioned, part of the LSI Nitro product line, and in all and in select SandForce-driven SSDs. Okay, so questions. I'm sure there's at least half a question out there. Yes, sir.
So typically the SandForce controller is using that extra spare area to boost performance and endurance, and that's kind of a variable floating target there. Now when you're returning that extra user addressable space, you're making that space user addressable. You're losing the benefit of over-provisioning and the endurance and performance increases. How does that affect the performance of the SSD as a whole?
Okay. Did everybody hear the question? So the question is, if Durawrite Virtual Capacity is taking that extra space that Durawrite alone would give back in over-provisioning, that over-provisioning would improve the performance and endurance of the SSD. And in this case, Durawrite Virtual Capacity is not giving that space back to the user, so what happens to performance and endurance? It actually stays as if it was 100% entropy. So in this case, Durawrite Virtual Capacity does not directly give you any performance or life advantage, but by the way, you can actually tune it, you can balance it. You can say, I want part of the SSD to give me advantage on performance because I have a certain requirement. I have a minimum threshold performance I want, so I'm going to take it up to that level, and then all the rest of that over-provisioning, I'm going to convert back to the user space, and so you can trade that. This is today more controllable at the manufacturing level, so an SSD manufacturer would say, this particular drive is going to give you X amount of life and this much extra capacity based on, let's say, an Oracle database, right? So they can spec that. And then if there was somebody at the, if they had a huge customer, let's say, they could literally just tweak that number for that particular customer. OEM deals, you know, you can name whatever you want.